So, this is just to recall what we have discussed previously. So, previously we have discussed the concepts of continuity, limit, partial derivatives, and then higher order partial derivatives. And we have also seen that the higher order partial derivatives, they may not be equal. The equality satisfies if both the derivatives, if all the derivatives are actually continuous. In that case, if both of them continuous at some given point, for example, x naught, y naught, then only the theorem says that mixed order partial derivatives. So that's a important result that they may not be equal, but equality happens when they are continuous. Also, we have seen the total derivative, total differential, and then we have seen the chain rules of partial derivatives. Okay. Now, it remains to discuss the other aspects of chain rules because we have seen that if we have a function w is a dependent variable and w is a function of x, y, and z. On the other hand, these intermediate variables they are a function of r and s. This x is a function of r and s. Y is a function of r and s. Other two variables, and also we have seen z is a function of r and s. In fact, there are many couple of examples, like many practical examples. For example, salary of a person. Another example was GDP of a country. So they are actually etc. In fact, you can say production cost. All these are actually of this type of functions. So W, if W is the salary of a person, then it will depend on several other functions. Annual salary, you can say. X, Y, Z, and some other factors can be there. Many other. Similarly, this is also kind of, we have seen that this is a function of x1, x2, x3, x4. Similarly, this is can also be like that. Now, why these are important? Because in reality, what we do is actually people wants to optimize their annual salary, they will try to optimize their of a country for as a whole. They will try to uh, increase or improve their GDP. On the other, yeah, for this case, people will try to, the managers will try to reduce, or the production cost they will try to minimize. So all most of the real life problem are actually several variable type. They depend on several variables. And then we have seen that the rate of change we have calculated, it is in terms of R and S. Now, what will be the rate of change with respect to, for example, dw del w del x, and what will be the rate of change del w del y? What will be the rate of change del w del z? So that means what we want to do is we want to calculate the rate of change of w with respect to x, y, and z. Okay, so for this we need to recall our famous rule, that is Cramer's rule. If a system of linear equations is given, system of equations are given, then the variables, these variables are calculated by this formula. That is determinant of the, this is delta 1, delta, here this is delta 2 by delta. Then we can see that this is nothing but, if we expand this derivative, expand this determinant, then we can see of this form. And it will be similar to the, if we have 3 by 3 system, 3 variable, 3 unknown. So this can be actually calculated. Now if you extend this situation here, so you can compare them as right hand side, for example, this is C1, this is C2, then this is, for example, A1 into del F del X plus, you can call it B1 del F del Y. Similarly, you can call it A2 del F del X plus, this is B2 del F del Y. Now we want to find out, so for example, here we are taking the case of only two variables. Okay. It can be generalized to up to three variables also. So let us first understand for two variables. So if this is the case, then we take the cross multiplication rule. Let us take this as variable. So this is our unknown now. So this is our unknown now. Okay. And then we apply the Cramer's rule. So on the top it will have this case. So from here you can write del F del X equal to this case by this one. So that is del F del U divided by, this is del X del U into del y del v minus del x del v into this is del y del u, and here we have whatever we have, we call it a, yeah, this one you have to write there. Similarly, you can find here del f del y in terms of, okay, here again you get, but this the denominator, it has a special name. This can be written in terms of a determinant, because if you write it, if you expand this determinant, what you will get, del x del u into del y del v minus this is del x del v minus into del y del u. So this particular determinant is called the Jacobian of the variables, and this Jacobian is actually denoted by of this form del xy. So this is the numerator values and these are the denominator values. The partial derivative with respect to u and v for both the variables x and y. Okay. Now, if we just try to simplify, this is nothing but del f del x is equals to, this is 1 by j. So if you actually apply the notation of Jacobian, so Jacobian can be defined for any variables. So with the similarity, you can see that this is nothing but this negative of Jacobian fx and then negative of del fxy. Okay. So we obtain the formula for this case is this one. Del f del x equals to 1 by j equals to this one. Similarly, we will find out del f del y equals to minus 1 by the Jacobian. Remember, this Jacobian is, this is the Jacobian we have, this is x and y, and then u, v. So this is our Jacobian. And then we have found this one. Now for first three variable case, the Jacobian will be defined by this. Now how do you remember this formula? Because you have to write this u, p and w. So these are the upper, the numerator variables. So that is why we will try to calculate the variables as so on the numerator we will have this first row will have the partial derivatives of u. Then the second row will have partial derivatives of v. In the third row we'll have partial derivatives of w. Okay. This is how we will actually, you can extend for n variable case, n by n order we will get. So in that case, this would be the Jacobian, and then you can actually find out how do we get the partial derivatives. In fact, this Jacobian is useful when you want to transformation from one coordinate to another coordinate. I think in the next semester when you will study multiple multiple integrations. So there also you will see the application of this Jacobian. So multiple integration in spherical coordinate, spherical and cylindrical coordinate. So anyway, let us look at some example that we can. So anyway, this is if this is the Jacobian, then is actually del x del x comma y comma z is there. And then we can write it here. Del of u del of p and w. So the Jacobian formula you remember. So row wise you will get the partial derivatives of x. So in the second row partial derivative of y. In the third row you will get partial derivative of z. The same thing can be taken as a reciprocal, the inverse. If you take, then you will get the partial derivatives of u, then the partial derivatives of v, and then partial derivatives of w. Now, if you remember the problem that I have given in the last class, so transfer, so that was the chain rule for polar coordinate. That if z is a function of w is a function of x and y, and here this x is also a function of r comma theta, and y is another function of psi of r comma theta. And then we have seen that it was asked to prove this relation holds. For example, if the question is find the left hand side, find the left hand side. Suppose this is not given to prove that this is. Then if you do this actually, then you will get this one. But if the question is find del f del x whole square plus del f del y whole square, then how do you find it? In fact, this relation is not given, for example, then what you will do? Then we will actually try to verify the same result with this concept with the help of Jacobian. So that means you need to find out the partial derivative with respect to x and y. That's the motive of application. In fact, this application of Jacobian you will see throughout your engineering life, and not only that, after that also, this Jacobian will come to picture. Whenever, for example, if you join some industries, then also you will find the application of this Jacobian. So this is the case you want to find out, or let us say, so if you have this x equals to r cos theta and y equals to r sin theta, then you calculate del x del r. This is cos theta, del x del theta, then it will become minus r cos theta and del y del r. This is nothing but r is gone, so this is sin theta, and then del y del r del theta. So this is r cosine of theta. Now we want to find out del, so del z del r. What is it? Here it is. Del x del theta minus from here. Yes, right. You're right. Sin theta. Yes, here we have fine. Yeah, right. Now we have del z. In fact, in place of z, you can write del f. So you are attentive. Yeah, right. Thank you for correction. So this is u, or let us write del x. So del x del r plus del f del y, then del y del r. By chain rule, in fact, chain rule we have seen this one, but we wanted to prove the other one without writing this. Actually, we want to use the formula of Jacobian. So whatever we have seen by the chain rule, we will try to find out the same result using the concepts of Jacobian. So for Jacobian here, what it will be? So to x, y, del r comma theta. So this is nothing but del x del r del x del theta. So first order partial derivatives of this x, and then first order partial derivatives of y. So this is nothing but we have cosine of theta minus r sine theta. Then here we have sine theta, and here we have r cosine of theta. So this is going to be r cos square theta minus of minus, this becomes plus r sin square theta. So this is nothing but r. Now if you remember the formula for del f del x, what was that? 1 by Jacobian into del, the Jacobian of del f comma y, then del r comma theta. So that was the formula that we have seen here. In place of polar coordinate, you will have r. In place of v, you will have theta. And similarly, for this one, we will have r and this is theta. So here we need to find out the value. So this is 1 by r. And if you try to find out this Jacobian, then what you will get? This is nothing but del f del r, and then del f del theta. This is del y del r, and then this is del partial derivative of del y del theta. So here we get 1 by r times, so this is del f del r, then del f del theta. In place of del y del r, we can substitute these values. So this is sine theta, and from here we get r cos theta. Okay. Now we want to find out this value. Square term is there. So we'll do this square term. But before that, we need to calculate the value 1 by r times cosine of theta into del f del r minus sine theta del f del theta. If you do this square form, if you square it, then you will get, this is a square. Okay. So let us write and try to simplify. So what we have now, so del f del x is actually, if you multiply by 1 by r, so this is 1 by r, then r cosine theta del f del r minus 1 by r sine theta, and we have del f del theta. So this r and this r gets cancelled. So you'll simplify it. Then r cosine of theta del f del r minus 1 by r sine theta del f del theta. Now if you try to calculate the square, so then you will get here square. So for this del f, okay, this is square, del f del x square is equals to r square cosine square theta del f del r square plus, sorry, no, this is minus, sir. Right. Yeah, this case it is cancelled. We have cancelled already. So r square will not be there. So minus 2 times, so cosine theta of del f del r, then 1 by r sine theta del f del theta minus, not this is plus 1 by r square sine square theta del f del theta whole square. So you can call it equation number 1. This will be used with the equation number 2 because we will have similar equation. So for this case, we will try to calculate the other equation. So how do we calculate the other equation? We need to calculate del f del y. It is nothing but minus 1 by j times we have del of f comma x and then del of u comma v. So that is in this case r comma theta. So if you have this minus 1 by r and this is we get del f del r del f del theta. So here we get del x del r del x del theta. So you get 1 by r. Now this is the case we do not have found, so let it be there theta, but this one we know this is cos theta and this is minus r sin theta. So let us try to expand this determinant and try to look at the value. So minus 1 by r is outside. So here we have minus r sin theta into del f del r minus cosine theta into del f del theta. If you just simplify it, then you will get this r and this r get cancelled. This plus negative minus, so this negative and this negative will be plus. So this is sine of theta del f del r, and then this is negative and negative, so this is positive. So 1 by r cosine theta del f del theta. Okay, so this is we have del f del y. Now if you try to take the square form, then you will get this value. So this is sine square theta times del f del r. Let us write of this form plus 1 by r cosine theta del f del theta. Then in the next equation we can write del f and del y whole square. So that is nothing but sine square theta into del f del r theta plus 2 times sine theta del f del r times this is 1 by r cosine theta into this is del f del theta, and then plus 1 by r square into cosine square theta into del f del theta whole square. So let us call this one as 2. So now adding these two equations, we get del f del x plus del f del y. So there we have 1 cosine square theta into del f del square theta del f del r. So this is our common part, and then the common part is del f del r of whole square into there we had cos square theta, here we have sine square theta. Here we have positive 2 into this time. In fact, these are multiplication, so you can rearrange them. So this is going to be 2 by r. This is r is there. Then sine theta cos theta, and then del f del r, and into del f del theta. So here we have the negative of this. This one and this one will get cancelled. And finally we have 1 by r square into del f of del theta. And again we have here, we had sine square theta. Now we have here in cosine cos theta. So here we can, from this we can write del square r plus 1 by r square del f del theta whole square. Hence the result is proved. So whatever we have done in terms of this r and theta, now if we differentiate with respect to x and y, then also we can find the same value. So it is actually giving us the same value, but the thing is the approach is different. And why this different approach is important? Because sometimes this question may not be asked in this form. Show that this relation hold. The question is, try to find out this one. Find out the value of this variable. So in that case, you have to find these values. In fact, if this is the case, then you can calculate in this way. If the reverse case is asked, try to find out the left hand side. Then you have to find out this. Okay. So these two concepts are different, but they will give the same result. Sometimes Jacobian, not only sometimes, in fact, throughout the career, throughout your life, you will see there are, it will come several times into the picture of the discussion. So in this way, you try to find out the other variable. So this is actually, for example, you can call it a example 2. So this is related to spherical coordinate system. So from Cartesian coordinate, we go to the spherical coordinate system. So in that case, what will be the governing equation? So this is the case, not governing equation. And in that case, we will find out actually the derivatives. So this transformation will be used in. So try to verify these results. If you get any printing mistake, then inform me. Similarly, this is another problem that the Jacobian, okay, j and 1 by j, this multiplication will be 1. So this is another important property of the Jacobian in this case. Now Jacobian, do not think that Jacobian is a rigid topic. Okay. Jacobian can be defined. Okay, this is a Jacobian in this case. You can write 1 by j also. In fact, for any other variables also you can define. But whenever you are defining, just you have to write down the numerator and the denominator properly. So another 2 practice problems. Try to verify them. Another some more exercise. Sorry, before doing that, let us mention some important properties of Jacobian. As already we have seen that this is actually Jacobian, and 1 by Jacobian will be 1. Second property says it is also applicable for chain rules also. So if you get any intermediate values, then you can actually multiply with the chain rules. The third property says if the variables are actually independent variables, if function u, v, w are three independent variables and x, y, z are not independent, then we will have this Jacobian as 0. So that is why when some, uh, in fact, it is you will see that two functions, when we will see that ordinary differential equation, okay, then we will see the Wronskian is a concept which actually gives us the independent solutions. So two functions are whether or two or more. Independent or not, that is actually defined by this Jacobian. So this is another application, because if they are actually dependent means what we have seen, that any of them can be written as in terms of the other two. So that is the meaning of dependency. If they are independent, then you cannot write them as a scalar multiple or some other thing. So that is why there is an example to functionally, this is to try. So functionally related or not, whether this u, v and w, these functions are related or not. So that is actually investigated by the Jacobian of this function. So if there is a relation, okay, if for this particular example, u is this one, v is this one, and w is this one. So you try to find the Jacobian here. It is Jacobian u, v, and w with respect to the partial derivatives with respect to x, y, and z. Now, if you try to find out, this is a 0. If this is non-zero, then we can say that these variables are actually independent. But in our case, for this particular example, so these variables are related, because if you try to look at the structure, then this w is actually xu, and from there you can write these variables are actually can be written as one variable is written as in terms of the other two variables. So for dependent case, we can write this situation, because w is dependent on u and v. But if this is purely independent, then we not have this situation. So this is one counter example. Let me write this as three. Now, so let me just keep the serial numbers properly. So this is 2. You can call it 3, 4, 5. Example. Let us call this as 6. So with this 6 example, and these are some exercises for your practice problem. So try to verify these results. Now today there is another simple topic, but you will see its applications there too. Sometimes we want to study the homogeneous function, the properties of homogeneous function. Okay. There is one important theorem called Euler's theorem for homogeneous function. Okay. So this is little bit isolated topic, but again we'll try to find out the connection between the other topics. So this homogeneous function is a function for which the power of each term is the same. So here you have power is n, degree of x is n. So joint power is here n. The joint power is here n. Similarly, for joint power is n, here also the joint power is n. So this can be called as a homogeneous function of order n, or sometimes we call homogeneous function of degree n. Okay, order n. If the degree of each term jointly, so here it is x to the power y to the power 0, and here it is x to the power 0. So these two actually always n. Okay, here you have y to the power 0. So if you can take this x to the power n outside, then this will be rewritten as this form. And here you get another function, that is phi of y by x. So the original function fx y can be written as of this form. If this is the case, then we also call this is another form of writing the homogeneity of this equation. For homogeneous equation, we have this freedom to write in this form. So if you take xn outside, then we can get out this form. Now similarly, so for example, this case, this is a homogeneous function of order 3. If you consider about this one, then this is a homogeneous function of order minus 2 by 3. Because we have not mentioned what is n. N can be negative. Order n. N is not mentioned whether it is positive, negative, or 0. So negative can be there. But for this function, you can see we do not have the liberty to write in this form. So that is why this is not a homogeneous function. There is another equivalent definition to homogeneous functions. In place of, so this is our given function f of x comma y. This is given. Now in place of x and y, you substitute lambda x, substitute lambda y. Okay. Now if you get this lambda times to the power n into f of x, then also we call it a homogeneous. So if it satisfies any of the three, then we call it homogeneous function. Similarly, if you can take y common, y to the power n common outside, then also if it is satisfying this relation, then okay, then also we get the homogeneous functions of degree n. So that is why we can also write for the three variable case homogeneous function, and this can also be written as of this form. So if you take x to the power n common, then the other functions will be y by x and then z by x. Now there is for more examples. So this is a function of degree of homogeneity is 0. So that means, in other words, it is not a homogeneous function. Okay. So related to this homogeneous functions, there is one important theorem which is actually known as Euler's theorem for homogeneous functions, and this is connected to the partial derivatives. In fact, this Leibniz theorem is not our part of syllabus, But if we have studied the Leibniz theorem, where is actually Leibniz theorem deals with the relation between the nth order derivatives. Okay. It gives us a recurrence relation for the derivatives of ordinary or partial ordinary differential derivatives. Actually, so in order to, in fact, it is actually Leibniz rule is particularly gives a relation between the variables. It gives us one recurrence relation for the derivatives of some order. So anyway, that is not our main goal. We have if a function f of xy is a homogeneous function of degree n, then it will satisfy the first order partial derivatives will satisfy this relation, and the second order partial derivatives they will satisfy this relation. The proof is actually included here, although it is not a part of our syllabus, but interested students can go through it. So if you don't understand, tell me, I will explain. So how do we apply this Leibniz rule in our case? So if one function is given of this form, then what we actually try to satisfy the relation. Okay. So for this type of, this is equality, or you can say equations with partial derivatives, then u is given of this form. So if you try to find out, cosine of u will be x plus y by root over x plus root over y. So from there you take x common, and here you get 1 plus y by x. And from here you take root over x common, then you get 1 plus root over y by x. So this is again x to the power 1 minus half here. So we get 1 plus y by x. And here you get 1 plus root over y by x. Now this is nothing but x to the power half of 1 plus, you can call it some g of y by x. It is a function. So phi of y by x, not g. This is phi of y by x. So this is a homogeneous function. So we get a homogeneous function of order half. So by Euler's rule, in fact Euler's theorem, this is Euler's rule or theorem? Euler's theorem. We have x times del f del x plus y times del f del y equals to n times f. So what is our f here? F is our cos u. This is our f. Remember, f of xy is a given function. So this is our u. So if we apply this rule then you get x times del f del x. In place of f, we substitute cos of u plus y times del f del y. In place of f, we substitute cos of u. And in place of f, n, we substitute half. So this is half. Then in place of f, again, we substitute cos of u, cosine of u. That is, again, we use the chain rule of cosine of u. Then you can use here del x. Sorry, del u del x plus y times del u cosine of u, then del y. Sorry, this is del u del y, half of cosine of u. So from here you get x into minus sine of u, and then this is del u del x plus y times again minus sine of u, then del u del y. So again we have half of cosine of u. Now if we divide it by sine of x times del u del x plus y times del u del y. So this is negative half times cosine of u by sine of u. So this is nothing but half of cot of u. So hence I think it is proved. If you go back and check the original problem, we have to show this one. So sometimes if these relations are actually some identity, the left hand side and the right hand side we have to prove, and the function is homogeneous function, then it becomes easier to calculate the derivatives. In fact, you can try to verify the second result also. Take the second order partial derivatives and try to verify these results. There are some, so this is problem 2. If this function is given, then we can prove it. Similarly, for some other example, if you have this function, the function is given. So this is a homogeneous function of or degree 2. Then using the Euler's theorem, you can get the relation for the first order derivatives. Yeah, so in this way you can also see some examples, try to verify them. Yeah, so this is for another example. You go through it, you will understand. This is for practice problem. Verify these results. So yeah, so that's all for today. If you have any doubt, you can ask me.